We're going to be looking at a very specific way to solve some types of quadratic equations. It's called the extraction of roots method. And every time I teach this I think, oh, going to the dentist and something about a root canal. But trust me, this is a lot easier and a lot less painful. Now the only way you can use this method is if you have a squared term that can be isolated. Remember, a quadratic has an x squared, an x, and then usually a constant. So this is where we're just looking for that x squared and not that linear term of just x. So we can see these four examples. We have x squared equals 81, we have an x squared here, we have another squared here, and another squared here. So how can we use what's called this extraction of roots method? Well, we have a process. We want to isolate the squared term. Then we want to undo that squared term by taking the square root of both sides of the equation. Whatever you do to one side, you have to do to the other. And when you put in a square root, you have to make sure you take into account the positive and the negative of a square root. And notice, since we are dealing with square roots, we're going to need to simplify the radicals. Sometimes we have fractions, so we have to rationalize those denominators. And then we get to solve the equation. So let's look at these four examples one at a time. Number one, x squared equals to 81. Now we could move the 81 to the other side, set it equal to 0 and factor, but this should be even faster. We're going to isolate the squared term. Well, this is the squared term and it's all by itself. So we then get to take the square root, because as you recall, the square and the square root undo each other, and so we have x equals plus or minus, because we always want to do that plus or minus sign, 9. And that's it. Now if you were to have set it equal to 0 and factored it and set each factor equal to 0, you would have gotten -9 and +9. And so this is a little bit less steps. Again, only works when you have just a squared term. All right, let's look at the second example. So the first step is to isolate the squared term. Now this is what we need to get by itself, just x squared, not the 9x squared, but x squared. So how can we do that? Well, we can add 23 to both sides, and we have 9x squared equals to 23. And again, I just need the x squared by itself. So how can I get rid of that 9? We're going to divide because it's being multiplied. Okay, once you have that squared term by itself, you think, what will undo that squared? The square root. So we have x equals, automatically just put that plus or minus sign, the square root of 23 over the square root of 9. But what is the square root of 9? It's 3. So our final answers are x equals plus or minus the square root of 23 over 3. And remember, that is two answers, the positive and the negative. So as you can see, I think this is a very easy method for certain types of equations. All right, on this third example, we want to isolate that squared term, which is just x squared. So I want to add 4 to both sides. Can't take the square root yet. This is not isolated, so we need to divide by 7. Now we can take the square root of both sides. So put that plus or minus. And what's the square root of 4? That's 2. But the square root of 7 is just the square root of 7. Well, I've got a square root in the denominator, so I've got to rationalize the denominator. That means we multiply by the square root of 7 over the square root of 7. So we have plus or minus 2 square root of 7 over just 7. So we want to make sure we take care of all those radicals and don't leave any radicals in that denominator. Now looking at this fourth example, now we have a binomial squared. Yes, you could FOIL that out and collect like terms, but then you could not use the extraction of roots method. I guarantee you this will be faster. So we have something squared, which is all of that, and it's already isolated. It's already by itself. There's no coefficients, there's nothing added or subtracted. So we can just take the square root of both sides. Now remember, the square root and a square cancel each other out, so we just have x minus 1 equals that all-important plus or minus. And what is the square root of 25? Just 5. Well, I still need to solve for x, so I need to add 1 to both sides. This is where you've got to be really careful. You can't just say 5 plus 1 is 6 and say plus or minus 6. No, you really need to separate this. And you need to write this as x equals positive 5 plus 1 or x equals negative 5 plus 1. Either write that out or say that in your head, and so we get 6 or negative 4. So this is one instance where you have a number where you actually can collect like terms. So be careful. So the next example is very similar to the last one. Again, we have a quantity squared. So that's already by itself. So I can take the square root of both sides. And again, the square root and the square undo each other. So I have 2x minus 10 equals plus or minus, but that square root of 12, remember, is 4 times 3, so we can take out a 2 and leave a 3. So this is where I'm simplifying those radicals. First chance I've got to do that. I need to solve the equation. I need to work a little bit harder to get that x by itself. So I'm going to add 10 to both sides. But those are unlike terms, so I can't really do anything with that, but I still haven't solved for x. 2 is being multiplied by x, so I need to divide everything by 2. So I have x equals, and notice that reduces, so I have plus or minus the square root of 3 plus 5. And again, unlike terms. Now, you could have also done this. Instead of dividing by 2 individually, you could have drawn just a big division sign. And then, remember, if all the numbers outside of the radical can be reduced, you would reduce, and you would still get the same answer. So either way is fine, either individually or all one fraction. Let's look at one last example. Right, so just like number 4 and number 5, now we have number 6. It has a binomial squared. It's already by itself, so we want to take the square root of both sides. And so just like we've seen, that square and the square root undo each other, so I just have 5x plus 3. I have that all-important plus or minus sign, but wait, square root of a negative, ooh, oh yeah, that's imaginary. Also, so I know I'm going to have an I. The square root of 28, that's 4 times 7. So I can take out a 2 and leave a 7. Don't forget, we can take square roots of negatives now. All right, so just like on number 5, I need to get x by itself. So I'm going to keep this expression and I'm going to subtract 3, move it to the other side, and then I'm going to divide by 5. So I have x equals plus or minus 2i square root of 7 minus 3 over 5. And again, you could have done it as individual fractions. You're going to end up the same way. It would have looked like this, plus or minus 2i square root of 7 over 5 minus 3 over 5. Couldn't reduce here, so either answer is perfectly acceptable. So again, this is a nice method, especially when you have some binomials squared.